Welcome to Linear Algebra. Today we are going to explore one of the most beautiful and surprising results in all of mathematics, the Cayley-Hamilton Theorem. Imagine if you had a complex machine and that machine came with a specific mathematical rule book describing its behavior. What if you could plug the machine itself into its own rule book and everything perfectly balanced out to zero? That is exactly what this theorem does for matrices. Let us dive in and see how this mathematical magic works. Before we look at the math, let us understand why this concept matters. Every square matrix has a unique fingerprint or DNA sequence known as its characteristic polynomial. Normally, we plug regular numbers into polynomials, but the Cayley-Hamilton theorem states something that feels almost like magic. Every square grid of numbers perfectly solves its own special algebraic equation. It is like a self-fulfilling prophecy where the creator perfectly satisfies its own creation. This means we do not just have to plug standard numbers into equations anymore. We can plug entire matrices into them and watch everything cancel out beautifully. Now that we understand what the characteristic polynomial represents, let us look at how it is formulated. The formula comes from subtracting a variable lambda along the main diagonal of our matrix and finding the determinant. In this equation, A is our original square matrix. The symbol lambda is a scalar variable, meaning it is just a regular unknown number. The symbol I stands for the identity matrix, which acts like the number 1 in matrix math, ensuring our dimensions match up. The theorem states that if you replace the unknown number lambda with the entire matrix A, the result is exactly the zero matrix. Let us see what happens when we change these variables. If the matrix A grows larger or more complex, this fundamental rule remains completely unbreakable. Before we prove why this works universally, let us see this with a concrete example. We are given a 2 by 2 matrix with the numbers 1, 2, 3, and 4. We are asked to find its characteristic polynomial and verify that plugging the matrix into it results in the zero matrix. We chose this standard determinant approach because it is the foundational step for the theorem. First, we subtract the variable lambda from the diagonal elements, which are 1 and 4. Then, we calculate the determinant by multiplying the diagonal elements and subtracting the product of the off-diagonal elements. This sets up our algebraic expression. Continuing with our calculation, we expand the terms we just set up. Multiplying the binomials and combining like terms simplifies our expression to lambda squared minus 5 lambda minus 2. This is our characteristic polynomial. According to the theorem, if we replace lambda with our matrix A, the expression A squared minus 5A minus 2I should equal the zero matrix. To check this, we first need to find A squared. We do this by multiplying the matrix by itself using standard row by column matrix multiplication, which gives us a new matrix with entries 7, 10, 15, and 22. Now we calculate the remaining pieces of our equation. We multiply our original matrix by the scalar 5 and we multiply the identity matrix by 2. Finally, we subtract these matrices from our squared matrix. Looking at the top left corner, 7 minus 5 minus 2 is 0. The top right is 10 minus 0, which is also 0. The same cancellation happens for the bottom row. The result is indeed the zero matrix. Physically, this means our specific matrix perfectly balances its own characteristic equation, confirming the theorem holds true for real numbers. Now that we have successfully used the formula, let us understand where it comes from by proving it for any general 2 by 2 matrix. This chunk of the proof is setting out to find the universal characteristic polynomial. We start by defining a standard matrix with arbitrary letters A, B, C, and D instead of numbers. This ensures our proof works universally. Just like in our example, we subtract lambda from the diagonal and calculate the determinant. By expanding the binomials and grouping the lambda terms together, we get a clean quadratic equation. Notice that the middle term is the trace and the constant term is the determinant of the original matrix. This sets the stage for our substitution. Moving forward, we substitute our matrix A into the polynomial we just derived. Remember, we must multiply the constant term by the identity matrix so that all terms are matrices of the same size. The mathematical reasoning here is to evaluate each piece separately. First, we multiply matrix A by itself to find A squared. Next, we distribute the scalar sum A plus D into every entry of matrix A. Finally, we multiply the determinant scalar by the identity matrix, which places that value exactly on the diagonal. The intuition here is that we are breaking down a complex matrix polynomial into manageable individual grids that we can easily combine in the next step. In this final chunk of the proof, we combine all the matrices we just calculated. We subtract the middle term from our squared matrix and add the final diagonal matrix. If we look closely at the top left entry, the A squared and AD terms perfectly cancel out with the negative terms, leaving exactly 0. This same exact mathematical cancellation happens for every single entry in the grid. Every positive term is matched by an identical negative term. The intuition behind why this works is that the matrice's own structure is perfectly balanced against its determinant and trace. This gives the final result, proving that the theorem is a fundamental structural property of all matrices. Let us take a moment to visualize everything we have just proven. On the left side of the diagram, you see our starting point, a standard 2x2 matrix A. Following the arrow, we substitute this matrix into its characteristic polynomial, shown in the central box. This box displays the core equation involving the trace and determinant that we just derived. Finally, the arrow on the right shows the ultimate destination. The entire polynomial collapses perfectly into the zero matrix. This flowchart beautifully summarizes what the theorem teaches us. It is a direct, guaranteed pipeline from any square matrix to absolute zero. So, we have proven that the theorem holds. This brings us to a highly practical application. Why does this matter? Finding the inverse of a matrix usually requires tedious and complicated row reduction algorithms. However, the Cayley-Hamilton theorem provides a clever shortcut. Because the matrix satisfies its own polynomial equation, we can use basic algebra to rearrange that equation. By isolating the identity matrix and multiplying through by the inverse, we can find the inverse matrix using only simple multiplication and subtraction. This transforms a difficult division-like problem into a straightforward arithmetic task, saving immense amounts of time and effort. Let us see this shortcut in action. We are given the same matrix from our previous example, and we are asked to find its inverse without using row reduction. We chose this approach because we already know its characteristic equation equals 0. The first step is to get the identity matrix term on one side of the equal sign by itself. We do this by adding 2i to both sides of the equation. Now that the identity matrix is isolated, our next logical step is to multiply every single term in this equation by the inverse matrix, A inverse. This will allow us to drop the powers of our matrices. Continuing with our algebra, we distribute the inverse matrix to every term. Why do we do this? Because multiplying a matrix by its inverse cancels it out, just like dividing a number by itself. When we multiply the identity matrix by A inverse, it just remains A inverse. When we multiply A squared by A inverse, one of the A matrices cancels out, leaving just A. And when we multiply 5A by A inverse, the matrices cancel completely to become the identity matrix. The equation simplifies beautifully to 2A inverse equals A minus 5I. We no longer have any squared matrices. To finish solving for the inverse, we simply divide the entire equation by 2. Now we just plug in the actual numbers from our original matrix and subtract 5 times the identity matrix. We subtract 5 from the top left and bottom right entries, leaving the off-diagonal entries unchanged. Finally, we multiply every entry by the scalar fraction 1/2. This gives us our final inverse matrix. Physically, this means we have found the exact matrix that reverses the transformation of our original matrix. And we did it entirely through basic subtraction, proving the incredible practical power of this theorem. Now that we have used this formula to find an inverse, let us understand where else it is applied. Why does this matter in the real world? Engineers and computer scientists constantly need to calculate very high powers of matrices. For example, in control systems engineering, predicting the future state of a robotic arm or an airplane's autopilot requires raising matrices to the power of 100 or more. Doing this by brute force multiplication would take too much computer memory and time. The Cayley-Hamilton Theorem provides a massive shortcut. It allows any high power of a matrix to be collapsed and rewritten as a simple combination of lower powers, making real-time computer graphics and modern robotics possible. We have reached the end of our journey. Let us reinforce the most important ideas we have learned. First, the Cayley-Hamilton theorem proves that every square matrix perfectly satisfies its own characteristic polynomial, effectively bridging the gap between matrix algebra and polynomial equations. Second, we saw how this elegant property provides powerful shortcuts, allowing us to find matrix inverses without tedious row reduction. Finally, we learned how it collapses complex, high-power matrix multiplications into simpler arithmetic, which is essential for modern engineering and robotics. You have now mastered the full scope of this incredible theorem. Great job!